Good morning. This is Exploring the Solar System Part 5, Solar Max. The Sun goes through cyclic periods of activity, roughly every 11 years, and at the moment we are close to a maximum in the activity, hence the title of this particular talk. So firstly, a reminder that the only safe time when you can ever observe the Sun is during a total eclipse, when the moon blocks the disk of the Sun and then you see the beautiful solar corona. At any other time, you have to be very careful about making any attempt to observe the Sun. You should never look at the Sun without using special eclipse glasses. For instance, there is an eclipse coming up at the end of this month on the 29th of March. About half the Sun will be covered by the moon. If you intend to watch that, make sure you're wearing eclipse glasses to protect your eyes. Using eclipse glasses for safety is something that everybody should be aware of. And it matters not whether you're young or old. In fact, it matters not what species you are. You should still protect your eyes. Some dogs can actually pull it off with a certain amount of style. Some dogs really just haven't got a clue how they should be wearing the specs. But just bear in mind that what I'm showing about images of the Sun should only be attempted if you've got the right equipment. Don't assume that you can just look at the Sun or grab a pair of binoculars and see what it is I'm showing here this morning. So our Sun is a fairly typical star. Stars can be categorized or catalogued, if you like, on this classic plot, a so-called Hertzsprung-Russell diagram, in which every star is plotted according to its luminosity on the vertical scale and its color or its surface temperature on the horizontal scale. And there's our Sun, not quite in the middle, but it's a relatively average sort of star. Its luminosity relative to the Sun by definition is 1, and you can see many stars are many orders of magnitude brighter, or possibly many orders of magnitude fainter. And in terms of the surface temperature is about 6,000 Kelvin, which again is somewhere in the middle. There are lots of colder stars or cooler stars on the right-hand side, with surface temperatures of less than half the surface temperature of our Sun. And there are many stars that are really hot, with surface temperatures much higher than 6,000 Kelvin. So in many senses, our Sun is a relatively average star, and we're about halfway through the Sun's lifetime. If we think about what's going on inside the Sun, we are fairly sure about some aspects of internal structure of the Sun. We know that there's a core where nuclear reactions are taking place, producing the energy, and we think there are layers within the Sun, a so-called radiative zone where the energy is radiating out from the core, and then it becomes unstable, and further out from that is a so-called convection zone or a convective region where there are quite clearly convection cells as the heat is being transferred from the inside of the Sun to the surface of the Sun. The surface of the Sun, the visible surface, is called the photosphere. That's what we effectively see, including with an eclipse filter. We will see the surface of the Sun as the photosphere. And we also notice that under the right conditions, we notice that some plasma, some ionized gas from the surface of the Sun, gravity is not enough to hold on to this plasma, and sometimes plasma leaps up from the surface, sometimes detaches completely, either in arcs like prominences or occasionally in so-called coronal mass ejections. What's going on in the core? Well, it's nuclear fusion. It's often simplified by saying, well, what we've got is 4 nuclei of hydrogen, in other words, 4 protons, fusing together to make the nucleus of helium, which ends up as 2 protons and 2 neutrons. That's a little bit of an oversimplification, because what's actually going on is a whole chain of reactions. But the bottom line is we can effectively start every second of the Sun's life. It starts with 620 million tons of hydrogen and converts it into 616 million tons of helium. And therefore, every second of the Sun's life, it is losing 4 million tons, the difference between 620 and 616. And those 4 million tons of mass are lost and converted into energy through E = mc squared. And that energy is responsible for all of the heat and light that the Sun generates. Of course, not just the tiny fraction which comes in the Earth's direction. All stars are a question of balance. If we think about what's going on, gravity is always trying to pull all of the mass towards the center, and we've just seen that at the core we have a radiation source from nuclear fusion. That produces a pressure pushing outwards, and that outward radiation pressure effectively balances the gravity pulling in. The core is very dense, and so it actually takes a long time for any radiation generated in the core to actually make it to the surface. It could take 100 or 200,000 years for a photon generated in the core to actually make it to the surface. Once it reaches the surface, any light from the surface reaches the Earth in only 8 minutes, but the journey from the core to the surface, because it's so dense, can be extremely long. It's effectively like a ball in a pinball machine. It's bouncing around in such a dense medium, it takes a long time to make any traction. How do we know what's going on inside the surface of the sun? Well, might sound a bit odd, but we can use sound waves. Sound waves can be used to probe inside the sun in much the same way that seismic waves on Earth can be used by geologists. By watching what happens after an earthquake, you look at how those waves travel around the Earth. You can use those to determine the internal structure of the Earth. And it's similar for the sun. We can determine, to some extent, the temperature and the density and the motion of what's going on inside the sun. And here, this is a slice through the sun, coloured according to how fast the sun is rotating. So you can see the red areas indicates that the equator of the sun is rotating with a period of about 1 rotation in 25 days. But notice that it's different at different latitudes. As we move towards the poles, it's a lot slower rotation, over 34 days for the period of rotation as we approach the poles. We haven't really got reliable data at the poles themselves because we haven't got many spacecraft that are looking at the North Pole or the South Pole of the sun. Notice that not only is it a function of latitude, it's also a function of depth. Different depths in the sun are rotating at different rates as well. That makes for a very complex and somewhat chaotic structure inside the sun. Once the light reaches the surface, or once the energy reaches the surface, that's the point at which the light is released and we see the surface of the sun. In white light, if we look at all wavelengths, the middle picture there, we see a disk. It's not necessarily orange, it's just been coloured to make it look pretty. The sun is essentially white light because it's emitting across the entire visible spectrum, but we will often see small blemishes, small sunspots, darker regions, which we interpret to mean if they're dark, they're emitting less light, so they are slightly cooler than the rest of the surface of the sun. If we look in specific wavelengths, for instance, towards the blue end of the visible spectrum or the red end of the visible spectrum, we can pick out particular wavelengths which are characteristic of certain elements that exist in either the photosphere or the lower atmosphere of the sun, and we can start to pick out particular detail. Because specific elements at different wavelengths are existing at slightly different altitudes in the atmosphere of the sun, we're picking out slightly different structure. So in this particular case, we can see the same sunspot, the same dark patch in the same location, but it's clear that we're also picking up other structures. In the case of H alpha, one of the wavelengths of the hydrogen atom, we're picking up not only features on the surface of the sun, we're also picking up features near the edge. You can see that we're picking up little spikes there where it appears that hydrogen plasma is being released from the surface and arcing up into the atmosphere itself. Sometimes hydrogen plasma is released completely from the surface, doesn't simply arc up and then fall back again, which often happens with prominences. Sometimes hydrogen plasma is released from the surface of the sun and effectively has enough velocity to obtain escape velocity from the sun and will fly out into the solar system. These so-called coronal mass ejections, or CMEs, if they come our way, they will hit the Earth's magnetic field. The Earth's magnetic field will protect us to some extent from the charged particles in a CME, but the material will often get funneled, or the charged particles will end up spiraling in the Earth's magnetic field and end up getting funneled towards the North Pole or towards the South Pole. There's a complex interplay between the magnetic field of the sun and the magnetic field of the Earth. Any charged particles that do make it to the North or South Poles will manifest as aurora. So last time, close to Solar Max, the one before that, this was nearly 20 years ago, more than 20 years ago, I took a trip to Iceland to see the aurora borealis, and the sky absolutely lights up with greens and reds in these beautiful auroral curtains that seem to hang there in the air tens or hundreds of kilometers into the sky, and you get a wonderful shimmering effect which isn't really caught in this static photo as these charged particles from the sun hit the atmosphere of the Earth. But when we want to study the sun, the easiest way to figure out what the sun is doing is simply to look at the surface. And we've been doing that for a long, long time. Now we have tools that can, to some extent, look at the interior of the sun. But for many, many centuries, we've been restricted to only look at what's going on the surface. So John of Worcester was a monk, and in 1128 he wrote this manuscript, and I'm not very good at reading Latin, but somewhere in there he says, "I saw this large dot on the sun." Now, whether it is actually as large as this drawing would indicate, we're not too sure, but it is possible for some sunspots to get so large they can be visible, perhaps at sunset, perhaps on a foggy day, obviously not using any telescopes, because 1128 was long, long before any telescopes were invented. In 1600, people started turning their telescopes to the sky, like Galileo, and Galileo started recording the spots that he could see on the sun. These are the spots taken on different days, and he deduced that it looks like the sun is rotating. These blemishes appear to be on the surface of the sun, and as the sun rotates, in a period of about a month or so, these spots appear to move across the surface and change. They evolve, they grow, they disappear. Other people weren't convinced as to whether or not these spots, these blemishes, were on the surface of the sun. A lot of people assumed that the surface of the sun must be perfect, surely, and therefore if we're seeing dots, how do we know they're not in the Earth's atmosphere and we're just seeing them as silhouettes against the disk of the sun? So there was some pushback against this idea that sunspots were an intrinsic property of the sun. For instance, there are drawings from a little later in the same century of people saying, well, I think the sun is a large garden and there are fires burning there, and if the fires burn with smoke, the smoke is what we're seeing in these things. But when we look at drawings that came in later centuries, we see exquisite detail from drawings made, in this case Langley 1873, when you realize that this is before we had the ability to take high-resolution photographs and high-resolution images of any kind. The fact that it's possible to use a telescope to project an image at such magnification, such that you can end up sketching the sort of detail that we can see in a sunspot like that, it is truly amazing, especially when we realize that even with current technology, it's difficult to get resolution higher than this. Human eye is very good at looking at detail, even fleeting detail that's only visible for a fraction of a second, and remembering it and drawing it, whereas photography or imaging tends to integrate and sometimes can blur out some of the detail that's in there. But now we have the ability to take images of these dark regions of the surface of the sun, these so-called sunspots, and you can see that we're getting fantastic resolution given that the sun is 150 million kilometers away. The fact that with telescopes on Earth or in space we can get this sort of detail allows us to start to get a handle on what is actually going on. Yes, this is a cooler region of the sun. The sun is at 6,000 Kelvin. We think those sunspots are something like 4,000 Kelvin. On their own, they would be blindingly white, but against the sun, they are cooler by a couple of thousand Kelvin, and therefore less light is coming from them, and so purely by contrast, they look dark. We think this dark region is simply because heat from the interior of the sun is finding it more difficult to come out in one of these sunspot regions, rather than the general background surface of the sun. But this is still an intense area of research to understand the structure of these spots and how it relates to the internal structure of the sun and the energy flow within the sun itself. If we have a look at this region in the background where we seem to see little cells, this granulation, when we take a video, we realize that this is effectively the same as looking at a pot of water, a pan of water, put heat underneath, you see the convection cells on the surface of the water. That's effectively what we're seeing here. You can get an idea of the scale of this. There's the Earth to scale there. So these individual convection cells might be the size of a small continent or a country perhaps, And it's also thought that these bright regions in between some of these convection cells are important. They're not just image artifacts of the way the images were taken. It is thought that these are quite definitely hot spots, very much hotter than the rest of the convection cells themselves. And it is thought that that's one of the mechanisms by which heat from the sun ends up getting coupled to the high temperatures, the high energies of particles in the solar atmosphere, the solar corona. When we look at how many sunspots are on the surface of the sun, this is where we tend to see the variation in activity, the so-called solar cycle. If we plot how many sunspots do we see as a function of date, we see this characteristic oscillation on an approximately 11-year cycle. The height of the peaks don't always go to the same level. The depths normally go to somewhere close to zero. In other words, the sunspots tend to disappear and then come back again a few years later and then disappear and then come back again. The data in red is a little less reliable because up to about the middle 1700s, people weren't making reliable daily records of how many spots were seen. So we've got an indication of what happened in the 1600s, but it's not quite as reliable as everything from 1750 onwards. It is curious to note that there appears to be quite a long period, more than 50 years or so, or at least 50 years or thereabouts, in which no sunspots were visible. And that's still a bit of a curiosity as to why the activity of the sun should apparently just stop for 50 years and then come back again. It did coincide with a temperature change on the Earth, but that is thought by many climatologists to be just a coincidence. This is the sort of period where, if you look through the archives, look through the historical records, there are times when the River Thames has frozen over, for instance, and there were frost fairs during that period. But that might simply be a coincidence that, yeah, they just happen to be at the same time. There's no obvious evidence that just because sunspots disappear on the sun, that necessarily means less energy is arriving at Earth. But this particular oscillation, this 11-year oscillation, we know the sunspot cycle has been with us for at least a few hundred years, but it is actually possible to get evidence of sunspot variation going back even further than that. That on the right-hand side there is the 400 years in that small blue rectangle. That's the last 400 years. We've been able to extrapolate backwards for millennia, not by observations of sunspots, because 10,000 years ago nobody was recording sunspots, of course, but it is possible to get a proxy of solar activity by looking at how much carbon-14 there is in the atmosphere. Carbon-14 is an isotope. It allows us to date organic material. Carbon-14 is generated from cosmic rays hitting the atmosphere. And the activity of the sun, we know, is correlated with the activity of cosmic rays. The magnetic field of the sun changes the number of cosmic rays that hit the Earth. And therefore, it can be calculated as a proxy what the solar activity was as a function of time for thousands of years. And although you don't necessarily see the 11-year cycle, we do get an idea of how the sun's activity has changed. And so we don't think the sun's activity has changed dramatically over the last 10,000 years, though there is some evidence that about 10,000 years ago it seemed to be more active, but then again seemed to go through a large minimum. If we come back to this original idea of an 11-year cycle, we can look at the very right-hand side and say, well, where are we now? This particular graph goes to, I'm not sure, goes to about 2020. If we look at that in more detail and blow up what's going on in there, we can look at the most recent data, and what we find is that there was a solar minimum in about 2020. And if we look at what's happening in the last few months, that's the black line. The purple line is a sort of average of what's been happening in the last few years. And the red line, the red curve, is a prediction of what was thought to be, this is the next solar cycle. Solar Max, it is thought, will happen during 2025. That's what was thought when the cycle started in 2020. But the data at the moment seems to be higher than the predicted curve. At the moment, the sun is a lot more active than we would have thought it was based on the prediction of what the solar cycles were looking like and our understanding of how the sun is put together. So it's a little bit early to predict, but looking at this black line, I had the feeling that maybe the peak is going to be a little bit later than they predicted. That might not be the case because the black line, you notice, doesn't go into 2025, it finishes in 2024. I need to find some data to add a few more data points to that black line to see whether it's starting to show an indication of coming down or whether it's still on its way up. It would be nice to think that we haven't hit solar max yet, because if we are on the purple line rather than the red line, that means we've got another year or two of very active sun, lots of sunspots, lots of activity, lots of possibility of aurora. And because the sun has been so active in the last few months, that's why we've been able to see aurora from the UK. You can nearly always see aurora from the North Pole and the South Pole, from the Arctic Circle to the Antarctic Circle, but it's relatively rare to see nice aurora in the UK, and it's only happened, this was a picture I took from my bedroom window in October 2024, it's unusual to see those sorts of colours coming this far south, and that's a function of the solar activity being so high just at the moment. We can ask ourselves, what's the difference between solar max and solar min? One of the big differences is what's happening with the sun's magnetic field. When we look, this is a model of what we think the magnetic field looked like based on observations of what was going on the surface of the sun. This is what we think the magnetic field looked like during the last solar minimum. And if we look at the sort of field lines, they're a little bit wavy, but we can sort of get the impression that, yeah, it looks a little bit like the magnetic field of a dipole, a little bit like the magnetic field of the Earth. There appears to be a polar North Pole brush and a South Pole brush, and some sign of equatorial loops there. Pretty much the same as what you would expect if you just took iron filings and sprinkled them around a standard dipole magnet. So that's what it looks like at solar min. It looks relatively dipole. But when we look at what's going on around solar max, it's an absolute mess. And we can ask ourselves, what do we think is actually going on? Why does the magnetic field of the sun change so much between solar min and solar max? Well, it comes back to what I mentioned earlier. Remember the helioseismology? By looking at what's going on inside the surface of the sun, we can tell two things: that the rotation rate of the sun changes with latitude, the equator spins faster than the poles, and it is a function of depth. If we ignore the depth just for the moment and think about the rotation speed depending on latitude, it takes about 25 days for the equator to turn once, but it takes perhaps more than 30 days for the North Pole and the South Pole to actually turn. So there's always this sort of shear, if you like, between different latitudes of the fluid sun. That means that if you were to hypothetically start with a situation in which the magnetic field looked vaguely dipolar, if we imagine that that on the left represents the magnetic field lines during solar min, looking very similar to the dipole field of the Earth, what's going to happen as the sun rotates? As the sun rotates, the magnetic field must be taken with it, because we're talking about a plasma, we're talking about ionized gas, and so the magnetic fields will flow with the gas. So if the equator is flowing faster than the poles, what's going to happen is as the sun rotates, the equator is going to get wrapped round faster than the poles move. And if you imagine one rotation, two rotations, three rotations, remember one rotation is about a month. So once it's done a few years of rotation, it is going to be an absolute mess of tangled magnetic field lines. And that is the key to understanding why the sun has the solar cycle, why it has maxima and minima. If we think about what's actually going on, what will this on the bottom right look like after the sun has done quite a few rotations? Well, it's difficult to take in the details of what's actually going on when you think about a rotating sun winding up and tangling a magnetic field, but I will simplify this as much as I can. That's my attempt to simplify it. It is extremely complicated, and people have been trying to understand the interplay between the rotation of the sun and its internal magnetic field. They've been doing that for decades. I remember when I was a PhD student, before doing my PhD, I was told, don't go into magnetohydrodynamics. It is the most fiendishly complicated thing. Magnetohydrodynamics, the dynamics, the motion of hydrogen plasma, ionized gas, in the presence of a magnetic field. And the magnetic field itself is a function of the motion of the hydrogen plasma. So it's a sort of self-interaction, And by the time you've got the different layers of the sun rotating at different speeds, at different latitudes and different depths, it gets a real tangled mess. But if we think about one of those little pictures from the previous diagram, we can imagine the magnetic field of the sun getting wrapped up by this so-called differential rotation, equator moving faster than anything else. Once you wrap these magnetic fields up, eventually they will kink and twist, and it will not be a nice regular rotation of the magnetic field around the core of the sun. At some point, we can see on this diagram that loops of magnetic field are going to pop out, just like taking a rubber band and twisting it and twisting it, twisting it. Eventually, you get kinks and loops. The same is true of a magnetic field. When the magnetic field pops out in a loop and breaks the surface of the sun, then that's when you get these magnetic field lines visible. And it's quite remarkable how spacecraft have now shown us these coronal loops, as they're called. We can see the plasma. If we choose the wavelength of light appropriately, we can see plasma glowing as it travels through these loops of magnetic field. And where the loop actually enters the surface of the sun or breaks free of the surface of the sun, that's where we get sunspots, these little yellow circles indicated there. And the bright points on the right-hand side, these correspond to the areas that sunspots are appearing on the surface of the sun at either end of one of these loops. It's also interesting to note that when we look at the magnetic field, which we can do with the Zeeman effect in spectroscopy, we can actually identify the magnetic fields of sunspots, and we find that the sunspots often occur in pairs, with one of them being a north pole, one a south pole. And they're different in the different hemispheres of the sun. Not only that, when we look at the solar cycle, when the sun's field goes back to something resembling solar min and something looking like a dipole field, the dipole is actually upside down. In other words, the field, the magnetic field of the sun reverses every 11 years. So strictly speaking, it's a 22-year cycle. But it's difficult to see this magnetic field, but it's possible with sophisticated spectroscopy to actually identify the magnetic field across the surface of the sun and map it onto the behavior of these coronal arcs and the sunspots themselves. It is possible for amateurs to have a go at solar observing. Again, don't do this unless you know that you are using optical equipment which is safe. One option is to take a telescope and filter the sunlight through a thin metal layer which cuts the light levels down by many, many, many orders of magnitude to the point where it's then safe to observe. And then you will be able to see the surface of the sun. You'll be able to see the individual sunspots, and you'll see them come and go as day goes by. As each day goes by, you'll see the sunspots in a different position as the sun rotates. So you're effectively looking at the photosphere if you simply look at white light and cut it down to a safe level. But one option is not to take the whole spectrum, but to only pick out one wavelength, for instance, the hydrogen wavelength, which can be done with a specialist solar telescope. This is done with a Fabry-Perot etalon in the middle of the telescope to give you a very high interference factor, which means that you only let through the H-alpha wavelength and essentially nothing else in the visible spectrum, and that allows you to pick out what is the hydrogen doing rather than what is everything doing on the surface of the sun. Then you are looking at a layer of the sun which is slightly above the photosphere. It's called the chromosphere, and that's the point where there's lots of action going on. So again, you still see sunspots, but you see a lot of structure around the sunspots. You can see the churning surface of the sun behaving, and you can also see these prominences on the edge of the sun bursting out from the surface itself. This particular telescope is one I've used. It's called a Lunt telescope with a 60mm front element. So it's by no means a large telescope with only 60mm diameter lens, but that has been used to take images of the sun. These are images I took last year, and you can't necessarily see the amount of detail in there, so I'll blow it up. I take an image of the whole disk of the sun, but here, if I've just taken that region and blow it up, you can see that you get an enormous amount of detail within the individual sunspots and these bright and dark areas around the sunspots. These dark filament-like structures are actually prominences which are coming up from the surface And in effect, we're seeing them in silhouette. It's an arc coming out of the surface, and we're seeing them silhouetted against the bright surface itself. So we can get an idea of the structure of the sunspots, the bright areas, the very energetic areas, the darker filaments that are cooler coming off from the surface. And you can literally watch these hour by hour. They don't change much from 1 hour to the next. They change enormously from one day to the next. And of course, you can't watch the sun continuously unless you are in a spacecraft. But it's still amazing to see how much detail you can get with only a 60mm telescope, as long as it's a specialist telescope designed to look only at H-alpha. And on the right-hand side, we can see a similar surface taken on a different day, but now the sun is very active and lots of prominences are coming out from the surface of the sun. If we look in more detail at that one on the left, we see again a huge amount of detail, and you can, if you wish, watch these. If you set up a telescope in the morning and watch it during the day, you see these prominences slowly change as these enormous plumes are thrown up from the surface of the sun. Remember that on this scale, the Earth would be just a tiny dot, a few pixels in size. The Earth would be perhaps about the size of these sunspots that you can see there on both of these diagrams. In addition to amateurs having a look, there are some very large solar telescopes in the world. One of the biggest collection of solar telescopes is actually on the island of Tenerife, and the one on the left there at the top of this large white tower is called Gregor. And when we take our students, our astrophysics students from the University of Liverpool, when we take them to Tenerife, we, if possible, show them the solar telescopes during the day if the students are awake, because of course they're working during the night. So here's a group of Liverpool students being shown around the Gregor telescope. There's Mount Tidy in the background there behind the head of the person that's showing us the telescope. There are other solar telescopes in the world. For instance, the DK Inouye Solar Telescope in Hawaii is an American telescope, and there's a new European solar telescope that will be coming online in La Palma in just a few years' time. So again, a concentration in the Canary Islands as well as Hawaii. But as in most other cases, it's really great if you want to do solar observing. It's really great to get above the atmosphere completely, not just on a high mountain or a high volcano. If you can get above the atmosphere, it gives you far more wavelengths that you can then access, not just the visible part of the spectrum. You can then go into the ultraviolet and start to see more energetic processes on the surface of the sun, which is why in recent years a number of different spacecraft have been used. Solar Dynamics Observatory has now been with us for quite a few years, and it has a number of small telescopes, each of which is looking at a different wavelength. So effectively, it has a continuous, every few minutes, it'll be imaging the sun at a dozen different wavelengths, each of which has been chosen to tell us something about different layers within the sun, the surface, the photosphere, what's going on just above that, what's going on in higher levels of the sun's atmosphere. And by using all of that information, we can build up a complete picture of how the sun is behaving, at least in the vicinity of the surface, even though we can't see inside the sun. And more recently, you might have heard about the Parker Solar Probe, which has been sent in an orbit such that it is getting very close to the surface of the sun, so it can do some extreme detailed views of particular structures, including those little white areas that I showed before in the granulation video. Are those the source of the energy that's heating up the solar corona? We don't really understand that, and Parker is taking a very close view of the sun. It's getting very hot when it gets close, so it's on a very eccentric orbit, so it spends most of its time quite a long way from the sun, and then every once in a while on its eccentric orbit it takes a dive close to the surface, takes data, and hopefully tries not to melt, because it is a very high temperature environment it's working in. There are lots of missions, there are lots of spacecraft out there that are observing the sun and the interplay between the sun's magnetic field and the Earth's magnetic field, so-called space weather. Are we likely to be hit by charged particles? Are we protected against charged particles? Do we have to radiation harden all of our satellites to protect them from emissions from the sun? Not all of these missions are necessarily looking explicitly to understand the sun, but that's part of their job, if you like. including, if you see in the bottom right-hand corner, even the rovers on Mars have some instruments to actually measure the solar radiation to get an idea of. Parker will tell us what it's like very close to the sun, and Curiosity and Perseverance on Mars will tell us what it's like further out in the solar system. So if you want to know more about what's going on in terms of how the sun works, there's a very nice NASA overview telling you all about what's going on inside the sun, as well as these various solar missions that I've been talking about, the Solar Dynamics Observatory, the Parker. ESA also has a solar orbiter, and on the ground we have in Hawaii and the Canary Islands very large solar telescopes as well. Thank you for listening.